Hello again to all my friends, Mr. Benjamin here, and
Mrs. Podlipski.
And this is our third video in our Systems in Action series. And this video is dealing with mechanical advantage. Does that say D, Mrs. Podlipski?
And.
That doesn't look like and at all.
And.
That's
that doesn't look like a B.
That does
Mr.
look like a
B.
B. Mr. B. Okay, fine.
Mr. B's getting lazy. Actually, it's because the iPad is currently running on 11%.
And that was Mrs. Terio's fault.
Yeah, I think she was probably playing a game or something at lunchtime. So we're going to try and make this a quick one. But first thing we want to do is recall what we talked about yesterday in our previous video.
What is work? Work is the effort spent when work is the effort spent when a force causes an object to move. So we always think about our box. If we pick this up, we have to do some work on that box to move it a certain area. We also have energy. What is energy? Energy is simply the ability to do work.
And both of those things are going to be measured in
joules. Our good friend James Joules.
James Joules.
Joules. Yes.
Perfect.
Remember that. And we have one more thing. Oh, kinetic and potential. And that comes from... taking way too long to erase all this stuff.
There we go.
Quicker.
So we talked about the different types. Yeah, do you want to do formulas?
Formulas.
Okay,
work.
So work is equal to force times distance.
And where do we get force if we don't have force?
Force you can calculate from what we did in the previous video. So, for example, force of gravity or weight is going to be equal to mass times the gravitational pull. So on Earth here, that's 9.8.
And it'll always be 9.8 on Earth because it's a constant.
It's a constant, right? So if we need to calculate work done, then you're going to multiply any force. So a force exerted, for example, on the box, and you're going to times it by the distance that it has traveled.
Times it. You sound like Miss Terrio. Multiply.
Sorry, multiply it, okay?
And the last thing we're going to mention?
Last thing we're going to mention is the different types of energy that we talked about. So we talked about kinetic energy, and we talked about potential energy. So kinetic energy is when something is in motion, it's moving. Potential energy is stored energy. So for example, if you are jumping off of a cliff and into a body of water, at the top, before you've jumped off, you have potential energy. So that's that stored energy. If you are now moving, you've already jumped and you're moving through the air, you have kinetic energy.
That's a horrible D. Anyways, potential is stored, kinetic is moving. We have to continue as we're running out of battery.
Okay. So, our learning goals today. So we are talking about machines. So we're going to expect that you're able to discuss mechanical systems and their ability to reduce work. So make it easier for everyone. So that's the purpose of these machines. We want you to be able to differentiate or tell the difference between input and output forces. So that's the effort and the load forces, and we're going to talk a bit more about that. And lastly, we expect that you are able to calculate, so yeah, we're dealing with numbers again, calculate mechanical advantage of a machine. And so we're going to talk about that formula
Which is really, really simple. It's actually a ratio, so there's no units, but don't tell Mrs. Terrio that, because she'll freak out on you.
She says, it's not a ratio.
So a machine is any mechanical system that reduces the force, we've heard that word before, required to accomplish work. So, for example, a nutcracker. This guy right here.
That's not the nutcracker I told you to
He's a nutcracker, though.
Right, but that's not what I told you to put in here.
Well, which nutcracker are you talking about?
Like an actual tool that helps you. So here's our little nut. So it's the tool that helps you to crack the nut.
You just put the nut in his mouth and crack it.
Okay, well, if you say so, but a nutcracker.
That's a nutcracker?
Well,
kind of looks like a robot arm holding an egg or something.
Hey, a robot might do that as well.
It would, yeah.
Some other examples, aside from a nutcracker, might be like a...
Again. So we're not sure what happened there, but the battery's low. So the last thing we mentioned was a ramp or a pulley system. So a ramp, very simply, can help you get to a higher distance, right?
Without having to jump or climb a wall.
Which is reducing the force, right? So you can just walk up here,
Yep. Makes it easier to do that
And a pulley
task.
system as well. I'm going to draw a little flagpole here and a flag right here. And our pulley system would kind of be like that. And you pull the string up and down, which helps the flag go up.
Yeah, so you don't have to climb all the way to the top of the pole in order to put that flag up on top of the flag.
That's an embarrassment, so I'm going to get rid of it. But the ramp looks pretty good.
Good.
The right ramp inside. Ramp. Good.
So that's any machine. Now we're going to talk specifically about simple machines. So simple machines are machines that require only the force of a human in order to run them. So for example, here we have a bike and we have a car. So which one do you think, Mr. Benjamin, is the simple machine?
Well, the car requires a lot more than just a human.
Yeah, so the car requires gas to run, and I don't think you'd be able to push your car along to make it work, and that's not going to make anything easier on you.
A short distance at least.
Okay, so the car is more like a complex machine.
That would make the bike.
And that makes the bike your simple machine, okay? Because you're going to be using human power, so you're going to have to actually use your legs and move the pedals to get that bike moving. Another example might be like a saw, like a hand saw, versus maybe a chainsaw. So chainsaw is gas powered, whereas a hand saw would be more of a simple machine, helps you to cut something in half without using something like gas.
There's a lot more moving parts in our complex machines, right?
That's right.
So keep that in mind. Benefits. What are the benefits of using these machines? So the first benefit we have is increasing the force. So you can spend a lot of time training with Yoda to increase your force power, or you can use a machine. Ha 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 ha.
Another Star Wars joke,
Yes.
I assume.
Well, yeah, Yoda, of course. You don't know Yoda? So examples of this are Nutcracker.
Not the ballet.
Yeah, brilliant ballet. Or something like a torque wrench.
Okay, so instead of having to actually unscrew it with your hands, you're able to use
Or your
torque
teeth.
or your teeth to actually increase the force and move that.
Another benefit is to increase the distance. So we talked about a ramp. That's easier to get up. And another way we can think about this is we often use stairs. And we use stairs to get to different levels. If we didn't have stairs, if we only had like a rope, for example, that we had to climb, that would be horrible to have to get up to a different floor.
It's
It'd
like
be
gym class all over again, right?
Which I think I was in grade 2 or 3 when we had to do that, and I couldn't do it. Everybody made fun of me. It was really bad.
Too bad you didn't have stairs.
I know. I could just
Might
climb
have
the
made it
stairs.
easier, right?
We have one more benefit, and that is to change the direction
Of a force.
of our force. An example of this would be a pulley. So we've already made an attempt of drawing that, so I'm not going to do it again. But think about flagpoles. Good old Canadian flag in here. That is a maple leaf somehow in some way. But yes, if we want to get our flag up to a higher level, we're going to use a pulley system instead of having to climb up that pole and waste our energy.
So you pull down on the rope in order to raise the flag. So it's changing the direction of that force and it's raising the flag up.
Beautiful. Inputs and outputs.
Okay. So input and output, this is an important concept to make sure that you understand. So input is the force that is applied. So this is the effort force. So for example, if you are working with a car jack, so you're trying to jack up the car so that you can change a tire, the force applied to the jack by the person's hand, that's your input force, okay, or your effort force. So that's the effort that's put in. The out force, or output, is the force that the machine applies on the object. Okay, so this is the load force. So we're expecting then that the output is going to be higher because your machine is going to make life easier for you.
Because that's the benefit, right? It increases.
It increases the force.
Force.
Okay. So our output force, if we're looking at our car jack, so our input is the hand on the jack trying to pump it up, and then the output is going to be the jack on the car, so lifting up the car. Okay, so that's the load force.
So mechanical advantage, this is pretty much what we were just talking about if we take your example of our jack. Now, the definition is the amount at which a machine can multiply the input force. So if you have a very small input force and you get a great output, that's a really good mechanical advantage. If you have a really, really high input and a lower output, that's not very good at all. You're like, why am I doing all this work if this machine can't do the work for me?
That's right.
Should we do a quick example?
Yeah, why not?
And we're going to remember to grasp the problem.
Do you think that our students know how to grasp a problem?
Well, my students should know how to grasp it because I told them how.
Do you mind going over this with mine? Because
The
I don't
G
know
stands
if they
for
know.
given. You list the given information because all questions are going to give you some information. If they don't, they're going to be very difficult to do. The R is required. All questions are going to you see, I just tried merging question and required. Required. All questions ask you information, so this is what the question is asking.
So that's your unknown.
Exactly. A, analysis. Most of the time we're going to use formulas for this. Different questions require different formulas. S is solution. This is actually doing the work. And P is paraphrase, which you will give us a written answer, a full sentence, telling us what to do.
So now your solution should include units, correct?
Units, yes, always.
Okay. So if you have just some arbitrary number and you're supposed to have a unit, make sure that you include it there.
Because it could be like 15 cows instead of 15 pounds, something like that.
That's right.
That makes sense. All right, let's get rid of all that.
Okay, so why don't we use our example of maybe jacking up a car?
Alrighty.
Okay, so if you are trying to jack up your car, say you're on your way to school and you get a flat tire, okay, you wouldn't want to have to lift your car. That would be almost impossible. So we're going to use a jack to lift the car. So let's say that we are putting our input, so our force in, is 250 newtons.
Did we mention the formula? I think I forgot to mention the formula. Did you mention that? But anyways, mechanical advantage is equal to force of the output over force of the input. Okay? Keep that in mind. Felt over Finn. So our force input is equal to
250 newtons.
250 newtons. And our force output?
It's 3,000.
That's a lot.
So that's what we need to jack up that car.
Required. We want mechanical advantage. MA. Analysis? Well, we gotta use our formula,
so
right?
MA is equal to felt over Finn.
F out, or felt over F in, or Finn. Solution. Let's do this work.
So
MA equals, and I'm just changing the numbers based on what I have, right? So our F out was 3,000 newtons over our F in, which was 250 newtons. And now we're going to get our answer of, what's that?
12.
12.
now, because we've got newtons over newtons, they cross out and it's a ratio, so you actually have no units for this. So mechanical advantage is a number that is unitless.
So we just told you to have the units, but this one doesn't have one.
There you go.
Now for paraphrase, I'm not going to write this out because I'm out of room, but we would say the mechanical advantage of that jack is 12.
Now, in an ideal world, so ideal meaning perfect world, we would have a high efficiency, okay? So every machine that we use would make our life 100 million times better. So how then is our world maybe not so ideal? How does the machine lose efficiency? Well, there's a couple of ways, but one big one is going to be through friction. Okay? So when two objects rub together, sometimes the energy that you've put in is then going to be actually converted to heat. Okay? So when two things rub together, they often get quite hot. And so that kinetic energy, for example, that we've got, instead of being converted into something useful, it's going to be lost through thermal energy.
Which is generally a waste, unless you want your machine to give you heat.
Yeah. So thermal energy sometimes is not going to be what you want, or usually it's not going to be what you want. And sometimes through friction, you're going to lose that energy. So generally speaking, you have about 5% of your efficiency of your machine is lost through friction.
Now that number can increase based on the complexity of your machine. So cars are really, really, really inefficient when you think about it. They're awesome, but they're not very good at the same time. Most of the energy you put into a car is lost through heat and friction.
And that's why you kind of have to have things like coolant, right? That's going to cool your engine so that it doesn't overheat and it's still working properly. So again, we can calculate this. We can calculate our ideal mechanical advantage, and usually we do this through like a ratio of distance. So for example, we've got our hammer here, and our hammer is being used to pull out this nail. So that's our little guy's hand. So he's going to pull the hammer this way, and that's the amount of, or that's the force that's going to be put into that work. So if we have a distance that's going to be moved, the distance in over the distance out, so how far this is actually moving, that ratio tells us our ideal mechanical advantage. We're not going to actually have you guys calculate this out right now, but just so you know that in an ideal world, this is how we can calculate an ideal mechanical advantage.
It's a nice hammer, by the way. Really nice.
Thank you.
Oops, that slide's not necessary.
Okay. So we're going to now give you a task. So your task is to comment either on the YouTube video for Mr. Benjamin's class or within our Google Classroom environment for my class. You're going to provide an example of a simple machine. Now, we don't want you to steal ideas from other students.
Or us.
Or from us, yeah. So you have to come up with an example of a simple machine. So a simple machine meaning that one that is powered by humans alone, so not gas powered or anything else. Okay, so that's your task, is to comment with a simple machine. And I think with that,
What do we say?
let's say thank you.
Thank you. Thank you
So,
for watching.
Thank you for
enjoying.
watching, and make sure that if you have any questions, you come with them ready to ask us tomorrow.
Bye now.
Bye.